Hi, my name is Cindy Onokalah, and I'm a senior here at UNCG. I do research as a Marquis student in Dr. Kimberly Petersen's Asymmetric Organic Synthesis Lab. In our lab, we work to synthesize specific enantiomers of heterocyclic chiral molecules. For enantiomers, you can think of your left versus your right hand. They are mirror images of one another, but they are not superimposable. Enantiomers have a chiral center. In this case, a chiral center is a carbon atom that is bonded to 4 unique groups. In the chirality section of my poster, I've used thalidomide as an example of a molecule with a chiral center. R thalidomide was previously used as an anti-nausea drug, whereas S thalidomide causes severe birth defects in pregnant women. These birth defects can be as serious as the development of children with limb deformities. While R thalidomide was regarded as an anti-nausea agent that was great for offsetting nausea in pregnant women, the body actually racemizes it to the S thalidomide, which causes undesirable side effects. The previous work section details work that was done by members in my lab group. They were able to synthesize various chiral heterocyclic molecules using a Brønsted acid. The Brønsted acid worked as a proton donor for prochiral diesters. R and S trip were used to synthesize lactones, dioxinones, morpholinones, and dihydrocoumarins. Beneath synthesis of lactams, my focus for research is detailed. I plan to use the trip catalyst to asymmetrically cyclize lactams with an indole moiety. Beneath target lactams, you can see gamma, or 5-membered ring lactams, as well as delta, or 6-membered ring lactams. Lactams are important and useful because they only require a small amount of catalyst to cyclize, they have high potential for enantiopurity, and they occur naturally with analgesic, antibiotic, and metabolic properties. I've chosen horsefoline as my representative molecule as it has an indole moiety, a lactam, as shown in blue, and a chiral center. On the far right-hand side, you can see my attempts to cyclize a gamma as well as 2 delta lactams. Reaction scheme A details the multi-step synthesis of the gamma lactam. The gamma lactam utilized the diisopropyl malonate, as you can see the diisopropyl groups in green, but it was not able to cyclize due to ring strain. In order to combat the ring strain of the 5-membered ring or gamma lactam, a 6-membered ring was attempted to be cyclized in scheme B. In scheme B, dimethyl malonate was used instead of diisopropyl malonate. The methyl group is shown in gold. While we anticipated the deprotection of the nitrogen, as in compound 27, a decarboxylation of compound 26 actually occurred. Due to this decarboxylation, TRP was not able to be utilized to cyclize a delta lactam. In order to combat this decarboxylation, the bulkier malonate, diisopropyl malonate, as well as no protecting group were used in scheme C, the key reaction. The synthesis of this reaction is still underway. I'm in step 2 of this scheme, and the results will be reported. Future work is detailed towards the middle and bottom of my poster. In the future, if scheme C is not able to be cyclized with TRP, I plan to run the key reaction again with alternate protecting groups. The presence of a protecting group will keep the nucleophilic nitrogen from reacting prematurely. I also plan to utilize the bulky malonate, diisopropyl malonate, as a means of combating the decarboxylation of the smaller malonate. I also plan to revisit reaction scheme B and attempt to remove the paramethoxybenzyl or PMB protecting group by other means. Thank you for viewing my poster.